Hi guys. I know some of us have been struggling with determining polarity in a molecule. So this lesson's just going to review that with you. So this is completely optional, you don't have to watch it. But for those of you that are struggling, it might be beneficial. So the tool that you need is your electronegativity table. And so I went ahead and copy and pasted it here to make it easier. Don't forget that up here it says D and it should actually be O, that's oxygen. That was a misprint on the thing. These are the compounds that I'm going to look at, or the molecules that we're going to focus on today. Actually, you know what? I am going to go ahead and add one more. There we go. Okay. So this is the part where if you think you understand what you're doing and you want to practice, then take these molecules and determine their polarity as well as which IMF it contains. For those of you that aren't sure, let's work through this. So the first thing that we need to know, and this changed a little bit from what was said in class, the old notes I've updated, and this will just make it easier so you don't have to remember quite as much going forward. But the items that we have are nonpolar, and in order to be considered nonpolar, we're going to have an electronegativity difference of 0 to 0.4. You're going to see us write this as change in energy because our electronegativity is telling us about how much our energy is changing. That's what that electronegativity is. Remember, the electronegativity is the amount of attraction between one atom's nucleus and another atom's electrons, and that attraction is energy. So change in energy, that's going to be our difference in our electronegativity. In order for it to be polar change in energy is going to be 0.5 to 1.9. This is where the change is at. In class, we said that polar was 0.4 to 1.9. That was confusing. I know that I said that we were going to do the whole 0.4 is polar unless it's blah, 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 blah. But we're just going to go with this way just to simplify it, make it easier. So 0 to 0.4 is nonpolar, and polar is going to be 0.5 to 1.9. The last thing that we have is going to be ionic, or our ion, and that's going to be anything greater than 1.9, so 2.0 and higher. So then with this, what we're going to do first, let's go ahead and look at our selenium iodide. My selenium is going to be right here. So that's going to have 6 valence electrons. And because it has 6 valence electrons, that means that my iodine is going to form a bond on either side. Remember that you can use your molecular shapes chart that you were given. That tells you the number of bonds. Well, selenium's going to form 2 bonds. It has 6, so it needs 2 more. And with our bonding regions and our lone pair regions, so we've got our 2 lone pair regions, and when we make our imaginary box, we've got 2 bonded and 2 unbonded. That's going to make it bent. So we do need to remember that. I'm just going to go ahead and get rid of that. And let me redraw this a little bit better. You can still draw it as the straight as long as you understand what the shape actually should be. I'm going to go ahead and draw it as the shape just so that way it doesn't confuse some of us. Okay? Because remember, my Lewis dots would be up there, but we don't need to draw them. So with this, when I look at selenium, selenium has an electronegativity of 2.4. Iodine has an electronegativity of 2.5. So my change in energy, my electronegativity difference, is going to be 0.1. And if you remember from up here, that clearly falls in our nonpolar. So these are going to be nonpolar bonds, which means that this will be a nonpolar molecule. So nonpolar. And since it's nonpolar, that means the intermolecular force involved is going to be LDF. If you need more information on that, then watch the video on the intermolecular forces that I posted. But for now, we're just going to go ahead and move on. So next I have CO2. So when I have carbon dioxide, my CO2 is going to form. Remember that carbon has 4, so it needs 4, and oxygen has 2, so it needs 2. So what's going to happen is my oxygen is going to form double bond on each side. Once again, if we do our whole square, that means that since there are 2 bonding regions and both of them are bonded, this is going to be a linear molecule, and that is going to play a very important role in just a moment. So when we look at this, we have that our carbon is 2.5. And we have that our oxygen is 3.5. So this is a polar bond, okay? Listen to what I'm saying. This is a polar bond. However, so in order to indicate a polar bond, we're going to draw a dipole. And the way that you draw a dipole is you draw an arrow pointing in the direction of the more electronegative atom. So in this case, my oxygen is 3.5. It's more electronegative, so my arrow is going to point towards the O. We're going to put a little tail down here because that makes it a positive, and that's telling me that when these are sharing, they're not sharing equally. And because they're not sharing equally, that's going to give this a slightly negative charge. It's spending more time with the electrons. And so that means that sometimes it's going to have a negative charge. Whereas my carbon, since it's spending less time with the electrons, is going to have a slightly positive charge. Now, this isn't a complete charge like in ionic bonds or ion-ion. This is just a partial charge, and that's what this little symbol is. The little symbol is essentially like an unfinished 8. Okay? So, we do have polar bonds here. However, because it is symmetrical, because it's linear and it has the same atoms on both sides, these are going to cancel out. And so even though I have polar bonds in my CO2, because they cancel out, this will be a non-polar molecule. So the bonds are polar, but the molecule is not because it's symmetrical. Now let's try our NH3. So if you remember, our nitrogen has 5 valence electrons, so it's going to have the hydrogen around here, and then remember it does have its 2 lone pairs up there. Once again, with our box, if you look at it, there's 4 regions. 3 of them are bonded, 1 of them is a lone pair. So this is going to be trigonal pyramidal. Now with that being said, I'm going to check my electronegativity for my nitrogen. And so when I come up here, I see that it's 3.0. I'm going to look at my hydrogen just while I'm here. My hydrogen's 2.1. So 2.1 and 3.0. So when I look at that difference, I'm going to have a difference of 0.9. So once again, this is going to be a, whoops, wrong direction. This is going to be a polar bond. But that's not the end of the story. I want to know, is this a polar molecule? First, I'm going to draw my dipoles. Remember, we're going to draw the arrow in the direction of the more electronegative element because that's where the electrons are spending more time at. making it a slight negative charge, and making my hydrogens a slight positive charge. So when I ask you to draw the dipoles, this is what I'm talking about. So then with this, since it's 0.9, this is polar bonds, but also importantly is since it is trigonal pyramidal, this is not going to be symmetrical. We have a lone pair up there all by itself. And so what that means is this will be a polar molecule. Now, my right component and my left component, since they're directly opposing each other, they're going to cancel out, which means my molecular polarity of this molecule is going to have an overall polarity in the upward direction. Okay? Because, so sometimes students get confused with this and aren't sure what's going on, and this is because I have a vector going this way, I have a vector going this way, so they're going to cancel out. And then the other vector that I have is pointing up, and there's nothing to cancel it out. So the overall molecular polarity is going to be up. H2O, good old friend Mr. Water. So when we have our H2O, once again, we're going to look at it. Now, we should all know that it's bent because most of you are used to drawing it that way. So my oxygen, and then it's going to have a hydrogen and a hydrogen. And keep in mind that's because it has a lone pair here and a lone pair there. So looking at our chart, 4 regions, 2 lone pair, 2 bonded, tells us that it's bent. So with this, I'm going to look at my electronegativity. We know that hydrogen is 2.1 from right there. And my oxygen from up above here is 3.5. And so now, if I do my math correctly, this should be a difference of 1.4. So this is going to be a polar bond. Let's see if our molecule is polar. Because we have the 2 lone pairs, this is not symmetrical. So that means that it is going to be a polar molecule. So in this case, we're going to point towards the more electronegative element. Don't forget to put in your partial charges. Remember that this is going to be partially negative because it's spending more time with the electrons. This will be partially positive because it's spending less time with the electrons. Since it is asymmetrical, it is going to be polar. When I look at these, keep in mind that these vectors, this vector is really 2 components. It has a right component and an up component. So this one also has 2 components. It has a left component and an up component. Okay, so this is math. This is why geometry is a prereq for this class and why algebra 2 is a concurrent for this class. So this vector is really made of 2 components. This vector is really made of those 2 components. These components cancel out, so all we're left with is our up component. So the overall molecular polarity is going to be up. Okay? I know you guys don't like when I put math and things, but math is a tool that was invented to help explain science concepts. We're going to come back to this one in just a second. I'm going to show you something else and then we'll come back to that. So NaCl is our last one. And if we remember this one seems familiar. This one is where we're going to form an ionic bond. So it's not going to be sharing. Remember, we don't draw lines between ionics. We only draw the lines between covalent. And so when I'm looking at this, I'm going to come up here and look at my numbers. I have 0.9 and I have 3.0. So my Na is going to be 0.9 and my Cl is 3.0. And so that's going to give me a difference of, did I do that right? No. Chlorine is not, yeah, chlorine is 3.0. Gotcha. And so because of that, that is going to be my ionic. Sorry, my brain is not working right now. 2, 3. Okay, there we go. So that's going to be a difference of 2.1, which we said that a difference of 2.1, or a change in energy of 2.1, is going to be ion, ion. So now, what if I ask you to rank these in order of strength? Well, what we're going to do is we're going to look at our polarities. So when we look at our polarities, we said that this was nonpolar, which was an LDF. When we look at this one, that means that this one is also nonpolar as an LDF. This one is polar, so that'll be a dipole-dipole. This one is a special dipole-dipole. So the van der Waals forces that you guys heard about before, you don't need to know that term for the quiz, but those include the dipole-dipole and this special one. So this special one is a hydrogen bond. And so even though it has an electronegativity of 1.4, when hydrogen bonds with certain elements, specifically when it bonds with fluorine, nitrogen, or oxygen, it's going to form a hydrogen bond. These hydrogen bonds are especially strong. For more information on that, once again, check out the IMF video. But this is going to be a hydrogen bond, and a hydrogen bond is 10 times stronger than a dipole-dipole. So that's why I'm bringing this up. And then my last one is my ion-ion with my 2.1. So if I rank these in order, I'm going to look at, I have two LDFs. Well, the LDF that's stronger, that has more force, is going to have a stronger attraction to its atoms. So I have a 0.1 and I have a 1.0. Normally that wouldn't play a role in just determining the IMF, but because I'm trying to compare the two, I am going to consider them. So if I want to rank this from lowest to highest intermolecular force, my selenium iodide is going to be the lowest because it's 0.1. Next is going to be my NH3 because it's 0.9. Then is going to be my CO. Oh, I'm sorry. I'm not even paying attention to what I'm doing. This was because it's an LDF. So those of you screaming at me through the screen, very good. Selenium iodide because it was nonpolar, and then I'm going to have my CO2 because it's nonpolar. So LDF, LDF. Then I'm going to have my dipole-dipole, which is going to be my NH3. Then I'm going to have my water, which is a hydrogen bond. And last but not least, the strongest of these is going to be my ion-ion. Now, these IMFs impact things like boiling point, melting point, state at room temperature. And so the stronger the intermolecular force, the more energy that's required to break that attraction between molecules. Remember that intermolecular force means the force holding the molecules together, not the atoms. The forces holding the atoms together are your ionic and covalent bonds. The IMFs, the intermolecular forces, are the forces of attraction between one molecule of a substance and another molecule of that same substance. Hopefully this helped. If it did, let me know. Press like so that way I know, and I will continue making these. Now you need to bear with me while I rehook up my computer to stop the recording.